All right, hello everyone, and thanks so much for coming today. Welcome to our ALMA webinar.
Just kidding.
So my name is Faith, and I'm the education specialist, and I'm joined here by my colleague Summer Ash, who's our education manager.
Faith, can you stop screen sharing for a second?
Sure.
Okay, and Tyler and Montana, can you turn your cameras on? Hi, everyone. Yes, as Faith said, welcome. My name is Summer. I'm the STEAM Ed manager, and this is the STEAM Ed team. So Faith just introduced herself. Montana, you want to say hi?
Sure. Hi, I'm Montana Williams, and I'm a tour guide here.
And Tyler.
Hey everybody, I'm Tyler. I'm also a tour guide and a PhD student.
And Faith is going to do the majority of the tour today, and I will see you when it comes time for our two guest speakers who both work on ALMA. So take it away, Faith.
Thanks, Summer. So so thanks so much for joining us today. And so we are staff who work in Socorro, New Mexico, and we typically give tours at our other radio telescope, the Very Large Array here in New Mexico. Right now, the VLA and ALMA are both closed for visitors. So we still wanted to find a way to virtually tell you more about them and give you a tour, even if you can't be here in person. Also, please do keep in mind that our internet here isn't always the greatest, so bear with us, please, in the case of technical difficulties. So, some housekeeping for how this is going to work. So our webinar is going to last approximately 1 hour. And if you have questions for us about any of the things that we're talking about, please use the Zoom Q&A feature at the bottom. So that is here on the right from where you should see it. And we're going to take dedicated times during this tour to answer any of the questions that you may have. And if you put your questions in the chat, it's pretty likely that we won't see them. So please use the Q&A instead for that. And then we'll also, in addition to answering some of them live, our tour guides will be answering some of them throughout the tour. So feel free to check and see if the answers have been posted there. And then please use the chat feature if you need to let us know about technical difficulties that we're having. And then also during the tour, we're going to be talking about a few things that you can find on the internet on various websites. So if we'll be posting the links to those things in the chat as well. And so the chat, as you can see, I know some of you have already been using it, is right there. And we will try our best to answer as many questions as we can, but if we don't get to all of them, we do have a feature on our website called Ask an Astronomer. And so you can go to this feature and you can search our archives and see if the question has already been asked. We've got questions about lots of different things about the telescopes, about the science. And if you can't find your question there, you're welcome to submit your own question, and the answer will probably be posted within 72 hours. So before we launch into the tour, we're going to spend a few minutes sharing an introductory video with you. So now just give us a moment while we switch screen sharing, and we'll share the ALMA video with you.
ALMA, in search of our cosmic origins. Located high in the Andes mountain range, the 66 antennas that make up the Atacama Large Millimeter submillimeter array, ALMA, are an imposing sight. Under one sky, more than 20 countries embark upon a scientific endeavor that can only be realized through collaboration. North America, Europe, East Asia, and Chile work together to answer humankind's fundamental questions. Northern Chile was chosen as the site for ALMA because the Atacama Desert is the driest in the world. Its atmosphere, almost devoid of water vapor, enables detection of some of the faintest signals from the universe. Over 16,500 feet above sea level and covering distances of up to 10 miles of the Chajnantor Plateau, the ALMA antennas work as a single large telescope. A supercomputer combines and synchronizes all of their signals in real time. Thanks to this engineering and scientific feat, we're learning about the cold universe, the secrets of planet formation, and the chemical elements that constitute the building blocks of life. Professionals from around the world work for ALMA, pushing the limits of knowledge every day. In Chile, about 50 staff members are based in Santiago, while another 200 work in shifts at the Operations Support Facility close to the town of San Pedro de Atacama. Most of the staff works in the offices, laboratories, and antenna control room of this facility at an altitude of 9,500 feet. Others ascend to the Chajnantor Plateau at 16,500 feet to maintain and relocate the antennas, among other tasks. Strict safety protocols are crucial under these conditions. Thanks to leisure and residential facilities, staff can lead a healthy lifestyle, playing sports and games, watching movies, enjoying nutritious meals, and resting in comfort. ALMA plays a key role in global astronomical efforts. Along with other radio telescopes, it allowed the first image of a black hole to be captured. Without ALMA, that goal would have been unattainable. The Chilean astronomical community actively participates in ALMA research and discoveries, using its 10% of observing time. The radio telescope also contributes to workforce development and supports national and regional scientific, technological, and outreach projects. An example of the latter are the thousands of visitors who tour the facilities each year. ALMA respects the local Licanantay or Atacameño indigenous culture, supporting educational and other projects in the town of Toconao and San Pedro de Atacama, preserving archaeological heritage sites, and protecting the unique flora and fauna of the region, to name a few initiatives. Mirroring the antennas that work in unison with one goal, under the same sky, the international collaboration that ALMA embodies continues the search of our cosmic origins.
All right, so now we're going to return back to our slideshow here and talk more about ALMA. So as the video mentioned, ALMA is located in a very high and dry location. And so the reason for that is that when we build Earth-based telescopes, the atmosphere of the Earth will interfere with the light that is coming to us from space. And so if we go in a location that's at a high elevation, then the air is thinner there, and that's at least lessening the problem of atmospheric interference. And so the array operations site, which is where the actual antennas are located, are, as it mentioned in the video, at 16,500 feet or 5,000 meters. And then we also choose a dry location because moisture and humidity in the air can further interfere with light coming from space. And so, as they said, the Atacama Desert is the driest location in the world, so that also lessens that problem. And so the Operations Support Facility, or OSF, as we call it, is where most of the employees who are at the ALMA site work most of the time. Very few employees are actually able to go up to the high site. If you want to go up there, you have to be physically tested and you have to take oxygen tanks with you. It's very very strenuous to be at that high of an elevation. Even the OSF, which is still at 2,900 meters or about 9,500 feet, is also pretty high up. So, but they have a residence area at the OSF where employees can stay, and buildings where they can work and eat. So this is where a lot of workers spend a lot of their time. And there are 66 antennas total of different sizes. 54 out of them have a 12-meter diameter, which is about 40 feet. And the remaining 12 are 7 meters, which is about 23 feet. And they each weigh about 100 tons. And they look different from each other because they're built by different countries, as I'll talk more about in a moment. So when you see wide shots of the whole ALMA array, you might notice that not all of the antennas look alike. And so we move the antennas to and from the OSF and the array operations site using transporters, which are named Otto and Lore. In our picture here, Otto is the one with the red accents and Lore has the green, and they each weigh 135 tons, which is 270,000 pounds. And when they move, they only have a maximum speed of about 20 kilometers an hour, which is about 12.5 miles per hour. And then when they're carrying an antenna, they slow down even more to only about 12 kilometers an hour, which is about 7.5 miles per hour. Since they're carrying an antenna, they want to move very slowly for safety purposes. So one of the really great things about ALMA is that it's an international partnership between several different groups. So the different groups involved are North America, specifically the North American part is the US and Canada and partially Taiwan. And they are all represented by the National Radio Astronomy Observatory, NRAO. And that's who our staff present here today works for, is NRAO. Then Europe is represented. There are 16 different countries that are part of the European Southern Observatory, or ESO. And then East Asia, which is specifically Japan and South Korea, and also partially Taiwan, is represented by the National Astronomical Observatory of Japan, or NAOJ. And then Chile itself, as the country that is hosting ALMA, also plays a very important role, and they have their own ALMA offices for employees as well, located in Santiago, which is the capital of Chile. And so every year, ALMA pays money to be able to use the land that they're on to the Chilean government. And Chilean astronomers are also guaranteed observing time on the telescope. And so we have some pictures of the different antennas here. Oh, I should also mention, by the way, too, this picture is a picture of the former president of Chile on the left and the former director of the National Science Foundation here in the US on the right. And so for the different antennas here, each of them were contributed by these different observatories who also contributed other things to this partnership as well. So NRAO gives about 3/8 or 37.5% of the total budget to ALMA each year. And we gave 25 out of these 66 antennas. So this picture over here is what a North American antenna looks like. And a few other, there's a whole long list of contributions that all these different observatories made, but a couple other notable ones that NRAO gave were the technical building at the high site, the array operations site, and the roads that lead from the OSF to the high site, and an optical telescope to help with pointing, and the correlator, which is the supercomputer that compiles all of the ALMA data. And then ESO also contributes 3/8 or 37.5% of the budget. And they also gave 25 12-meter antennas. So this right here is one of the ESO antennas. And in addition, they also contributed Otto and Lore, those two transporters I showed you in a previous slide. And the OSF buildings, both the technical building and the dormitory where the staff stays, and the road that leads from the entrance of ALMA up to the OSF. And then NAOJ contributes the remaining quarter of the budget, so 25%. And they gave the remaining 16 antennas. 4 of them are also 12 meters. So over here we have what the Japan-made telescopes look like. And then also all 12 of the 7-meter telescopes, which are shown right here, were given by NAOJ as well. And so their 16 telescopes, these 4 12 meters and the 12 7 meters together make up what's called the Atacama Compact Array, also known as the Merida Array, that's in the center of ALMA. So it's part of ALMA, but it can also do its own separate research and to look at objects in the sky. And in addition to providing this, they provided a correlator specifically for this smaller array and other aspects to make this array run smoothly. And I'll also mention too, before we move on, that this picture in the middle shows all 3 of the 12-meter antennas next to each other. So on the left here, this is a Japanese antenna. This one here is a North American antenna, and this one is a European antenna. So now I'm going to hand it off to my colleagues, and Summer is going to be talking to our guest speakers. And so we're going to start with Summer and our first guest speaker, Loreto.
Thanks, Faith. Loreto, you have your camera on. Let me get you on screen with me.
Can you hear me?
Yes, I can hear you.
Great. Hi,
So,
everyone.
welcome.
Thank you.
Loreto, you are talking to us right now from our NRAO offices in Charlottesville, Virginia, correct? Or your home, obviously.
Right
Your
now, my
office.
home. Yes.
And you are an assistant scientist for the North American ALMA Science Center, correct?
That's right.
What does that mean?
So basically, I'm an astronomer. So I have a PhD in astronomy, of course, and I work for the group within NRAO, so the entire National Radio Astronomy Observatory. I work for the group that is in charge of all that it has to do with ALMA, basically. And in particular, in my group, we work with the community. So we take care of all the, we provide services for the community, specifically to astronomers that are using or that want to use ALMA.
Nice, that's great. And so I want to get back to that, but I also want to hear sort of what is your career path and how did you get into astronomy in the first place?
Excellent. So I'm Chilean. So I was born in Chile, in Santiago. And I studied, I started doing an undergraduate career in physics, in applied physics. So I studied in the Universidad de Santiago de Chile, USACH, and I spent 6 years there. I actually, funny fact is that I did, USACH doesn't have astronomy, or at that moment it didn't, and I decided just to do something to do with materials, so ceramic materials. So understanding the properties of materials, you know, ceramic materials. So nothing to do, you know, with astronomy. But then I went to, I got a Fulbright scholarship to do a PhD here at the University of Virginia. So actually here in the same place, Charlottesville, Virginia. So I spent 6 more years there. And then I went back to Chile for 2 years as a postdoctoral researcher. So basically a full-time astronomer to work for the observatory. And after that, I was 2 years there. And then I got this permanent position here at, in Charlottesville as an assistant scientist.
Okay, so let's go back to the astronomical community that uses ALMA and how you help them. What are some of the things that the community sort of needs help with?
Right.
Are you working with them once they have already gotten successful proposal accepted?
That's actually a very good question. In the community support team, we help the astronomers even before that. So from preparing their proposal to understanding the outcome of ALMA. So basically the images that we provide we provide support so that they can do their research. And so we provide in every stage of the way, we provide help, like from we go, okay, so I said before that they propose, during, right? So after they propose, and if they got accepted, we communicate with them before the observations are done, during the observations, after the observations, and in the future as well. And that's not only, we also help investigators that don't necessarily, have their own ALMA data, but astronomers, that they can go into the observation in the archive, which is where we store all the data that it's public. And so we also support the investigators that do archive research, that we call.
Is ALMA the same? I know with the VLA, we say, or the observers themselves have 1 year for the data proprietary to themselves, and then it becomes public. Is that the same with ALMA?
Yes, that's the same, although, and maybe Adele will help me here, but there is a special type of proposal that it's discretionary time from the director's discretionary time, which is a project that you submit anytime. So anytime you say, hey, you know what, we discovered something very, very cool and very, we need this now. So please, give me time to observe this with ALMA, because ALMA is so great, right? And it can give me, all this new information. And I think for them, once they get it, I think they have less time, I think 6 months or something, but the rest of them so as soon as you get your products, your observations done and delivered to you, you need to, it's 1 year since that date, then it becomes public.
The video that we played at the beginning mentioned that, I think it said that all the universities in Chile, or the astronomy departments in Chile, have 10% of time on ALMA. Yeah. And then is the remainder split 3 even ways between the international partners? Right, so it's not actually even between Europe and North America. They are even, but then East Asia has a little bit less. And then Chile has 10. So East Asia has more, I think it was 20 or something like that, 23, and then 33 for Europe and North America. Got it, thanks. So how did ALMA become part of, maybe not the origin story, because I don't want to put that whole pressure on you. I don't know if you know it, I don't know it. But how did ALMA become involved or join in the Event Horizon Telescope observations? Actually, I don't know the origin, but it makes sense. All these single telescopes that were involved in the Event Horizon, that are part of the Event Horizon telescopes, they all share the same frequency range that they observe, right? And so the more they have, the better. And right now they are thinking in expanding this, right? But ALMA had the perfect location, right? I'm going to share a picture right now of the excellent, Event Horizon telescope for people that don't know. It's worldwide network of radio telescopes. Right, and ALMA, it's key, right? Because it gave a large amount of antennas to detect something. So the more antennas you have, the better. And most of the other places are single antennas, right? So they are normally larger than the antennas that we have in ALMA, but we have many more, right? So we can cover, that. But yeah, at the end, ALMA proved to be essential to the observation. People have seen, images that so without ALMA and with ALMA, and it makes a difference. Yeah. So go ahead. Were you there? While this was being observed? So yeah, one of the things is that while I was in Chile as a postdoctoral researcher, we call it ALMA Fellow.
we went to the observatory as astronomers on duty on shifts. So basically you go there for a week, spend a week observing, and then go back home. And in one of those times, I was lucky enough that they were doing this campaign. So we observe in VLBI mode, with long baselines mode, so connecting to these other in campaigns. So there are weeks, a few weeks where, the telescope is exclusively observing, with this technique and together with other telescopes. And I was lucky enough to be there on one of the first few days. And so, yeah, I was there like I think they observed this in April 3rd, 5th or something. So I was there on one night. I was like communicating with the other team saying, hey, everything is going okay here in ALMA and things like that. But very tangential, right? Like, I mean, nothing like, there were other people from the campaign actually overseeing this, but I was on the shift at night, so they went to sleep, right? So I was there, I wasn't alone. I was with someone else. I don't remember. I think it was Jim Bratz, another NRAO scientist. So pretty cool.
For people that might not understand how we got to this image, can you describe just a little bit of what we're seeing?
Yeah, sure.
Galaxy.
So there is a nearby galaxy that it's called M87 that has in the center a very supermassive black hole. And they have been observing this because early in the days they found what you see in the top image, which is an image of the radio emission at 1.5 gigahertz taken with a VLA, and they found this jet, and so collimated and all, and then with the years, they started observing it with what we call the very large baseline interferometry, where you combine when you use this technique that the EHT is using. So combining signals from from telescopes that are very separated among that are spread on Earth. And they started observing, and they tried, so these are different, this is a lot of years, right? And so they went and you can also go, so they observed at 1.5, and then the second one from the top to the bottom, the second one is at 43 gigahertz, so higher frequency, but at the same time, higher angular resolution. And so they went there. And so at some point they observed these, it says GMVA, that's also done with ALMA. I am not so sure. It probably has less telescopes. I'm not so familiar with the GMVA.
Yeah, me either.
But basically then they jumped into the EHT, and that's the best resolution that we have ever been able to achieve, right? And to observe something like this. So yeah, so basically they knew that this source had a very central source, peaked in the central source in the center, that it's bright, because to use this technique, you need to observe things that are bright. And so they went there, and so that's how they got the EHT.
Yeah, that was really exciting. Okay, so before I let you go, just right now, I wanted to ask you if you had a favorite sort of astronomical source one that ALMA has looked at, or you even have used ALMA to look at.
So my favorite source, and this is a source that I met while in grad school, it's called ARP-220. ARP-220, and it's a merger galaxy. It's a galaxy that is very luminous in the infrared. This is an optical image using Hubble, so an HST image as a combined, so it's different filters. And the first thing that you see is that it has a weird shape. It doesn't look like the typical, Milky Way type of galaxy. It has some like plumes to the side, and that we call, tails, and that tells you that this is an interacting galaxy. Then the second thing that you see is something, brownish crossing the center of the galaxy, and that's actually a dust lane. And actually this source is so obscure that you cannot see what is happening in the center unless you go to frequencies like the ones that ALMA covers or the ones that the VLA covers. And so I studied this galaxy with the VLA during my PhD, and at the end of my PhD, I studied it with ALMA as well. So yeah,
and so this is a
yeah.
zoom in then to that
Right, so-
center we couldn't see before.
Exactly. So the background image here is, again, it's a single wavelength HST image where you see even more how much dust there is. And then in the center, in a zoom in version, you have in yellow, it's the continuum emission. So basically just the light that we see from what is happening there. And then in red and in blue, it's an outflow. So a material that it's, being ejected, right? And that's what we call is the Western nucleus. And that's a nucleus that in every sense is mysterious. It's very compact, it's very energetic. It stands out in any physics that we've studied. It stands out from, the normal physical properties in galaxies in general. And we found this outflow with thanks to ALMA. So we knew that there was an outflow in this particular object, but we didn't know how it looked, not where it was. And with ALMA, we were able to detect this outflow imaging it, for the first time, and found that, it's really collimated, so very narrow. So we're talking about things are these two nuclei here can fit into the central molecular zone of our Milky Way. It's very compact. These things, it's 400 parsecs separated, the separation. And that's very, very close, very compact. It fits in the center of our galaxy. But these are two nuclei of, the early, so this is, as I said, it's a merger. So these are like the nuclei of these two galaxies are emerging, and then they will become one at some point in the future.
Oh, very cool. I love the multi-wavelength astronomy because
yes,
you look here and you have no idea that this is happening in the middle.
Exactly. Yeah, that's the beauty of, studying these objects, astronomy in general, right? If you look at it with just one type of eyes, it's not going to be enough.
Yeah. Okay, thank you, Loreto. We will definitely bring you back for some Q&A and more discussion in just a little bit. But
Perfect.
Right now, I'd love to switch to Adele. So if Adele, you would turn your camera on, and I will stop sharing this. I love that picture of you, Adele. We'll come back to that. Oh, do you want to turn your microphone on? Perfect. All right. So welcome. I love that you've totally dressed for this. Is that your official? Is that what you get issued when you are the astronomer on duty?
This is an official, unofficial ALMA shirt from back in the day before there was ALMA products, and one of the other astronomers created some shirts for us to wear when we were on shift. So we used to wear these back in 2012, I think it was.
Yes, that is right when ALMA first came online, right?
Yeah, exactly. That's the inauguration, or the first opening of ALMA officially was 2013, I believe, March.
And so you are also in Charlottesville, and just like Loreto, you are also a assistant scientist and have also worked as the astronomer on duty at ALMA.
That is exactly right. Loreto and I followed sort of parallel paths to getting to finally share an office at the NRAO offices in Charlottesville, which we would be doing if we were working at our offices right now. But of course, we're now in our home offices. So hi, Loreto. I haven't seen you in a little while, but it's fun to gather here anyways.
And how did you first get into astronomy?
Yeah, so I am from Texas originally, and I went to college at Middlebury College in Vermont, and I studied physics, but I also was really interested in languages and traveling and international projects. And so actually I studied abroad my junior year and had my first internship at an observatory in Chile. And that's when I learned a lot about the international telescope projects in Chile. And I became really excited and enthusiastic about studying astronomy so that I could work for international telescope projects. So I finished my physics undergraduate degree. I had been studying Spanish at the time as well. And I decided that I wanted to study astronomy in graduate school. So I went to graduate school at Yale University for astronomy. And just like I said, I sort of followed this parallel path with Loreto. Actually, in grad school, I had a Fulbright fellowship, but to go to Chile. So Loreto came from Chile to the United States. I went from the United States to Chile. And I was able then to do part of my PhD actually at the ALMA Observatory. And I spent about 1.5 years down there working on some research of my PhD and also learning about how ALMA was working just in those years that it was getting started, 2012, 2013. And when I finished my PhD, I was looking for astronomy jobs all over the world, and ALMA was really a unique opportunity at that point to get to work for. And I landed a position for the European partner of ALMA, the European Southern Observatory, a postdoctoral position that took me down to Chile for 3 years to work at ALMA. And that's when I met Loreto, actually. And we worked on the same campus, basically, in Santiago de Chile, and took shifts at ALMA as well. And then, and we both applied at the same time for the position that we have currently at NRAO. So then I think we both realized, wow, this is such a cool opportunity. I want to keep working for ALMA. And it's a neat way to see ALMA from all the different perspectives, to come from Chile and then go work for the same project, but from North America. So now I'm working for NRAO. I've been here just over 2 years and based in Charlottesville.
I love the synchronicity of the two. So you mentioned that while you were in Chile, so you spent some time actually in Santiago, kind of in the offices there, but when you spend time up at the observatory, you're not at the high site, correct? You're at the operational science facility. Is that what it's called?
Correct.
OSF.
Yep. OSF is where most of the operations of ALMA are conducted. And in the video, we saw that the OSF is located just under 10,000 feet of elevation. And that's just kind of the level where you can function like a normal person. So it makes sense to do as much as we possibly can at that facility. And we can actually control the telescope from there. And so the astronomers spend most of our time when we're on shift at that site, at the 10,000 foot site in the control room. And we go up to the high site in the background of my screen here, just to visit, to get to see the antennas, because it's amazing to see them working together. And sometimes we can take some, special guests up to the top, but it's a difficult trip to get up to the high site at 5,000 meters. And yeah, you need to take some oxygen, you need to take it kind of slowly, but it's a really nice view. So I try to go as often as I can, maybe once per shift, I try to get up there.
How long are your shifts?
Yeah, our shifts are 8 days. And so we fly from Santiago to a city in the north of Chile called Calama. And it's kind of the central mining zone of Chile. And from there, we take a bus for about 2 hours over to past a small town called San Pedro de Atacama, which is this amazing touristic area where you see lots of unique environmental features and a lot of interesting animals. And from there, you go up the side of the mountain and you arrive at the ALMA site, and you get this awesome view of the salt flats. So those 8 day shifts, I mean, we work a lot. You work basically 80 hours within your 8 day shift. You're working kind of like 2 weeks of work in 8 days, but it's a really fun experience, actually. It's a unique opportunity.
And what's the difference between, so you are an astronomer on duty and you're in the control room, but you're not a telescope operator, is that correct?
True. So the astronomers on duty and the telescope operators, we all operate the antennas from the control room. And there's generally about 2 astronomers on duty and 2 telescope operators sitting in that room together with like 12 computer screens that you can kind of see all of the control of the antennas at any given time. The telescope operates 24 hours a day, 7 days a week, with some shared time for engineering projects and some computing projects. But basically that means that we need humans in that room to operate the telescope 24 hours, 7 days a week. And so we work on shifts like 8 to 10 hours with a little bit of overlap so that you can kind of clue in the person that's on the next shift and the antennas are just running the whole time. You don't want any downtime. You want to take full advantage of every minute in case, you know, there's a source going up right at that time. So the antenna operators are kind of running the machine of the telescope. So they're making sure that all the antennas are on, they're making sure that everything's functioning properly, and they're checking on the status of all the equipment. And the astronomers on duty were choosing which astronomy projects to observe at any given time. And we get a lot of help from this computer program and algorithm that actually Loreto is responsible for at this point, the scheduler. And so it'll basically, it's sort of like if you set up a really elaborate Netflix queue for, you know, several days at a time, and you could see like, what do I want to watch next? But, you know, you're constrained in astronomy by what sources are up at any given time. And we're even constrained by the weather. So if we have really clear skies with no humidity, then we want to observe certain projects at that exact moment. And so the scheduler helps us balance all these factors and decide what to observe at any given time. That's the astronomer's responsibility, to monitor the scheduling and then double check that the data look okay after we make an observation.
With the VLA we have, well, the VLA obviously would love to have antennas as scattered and filling out a circle as ALMA does, but obviously it was a compromise of money and technology at the time. But we have 4 fixed configurations. How many configurations does ALMA have, or how many different ways can you have those antennas positioned?
We have defined about 10 configurations, but the really cool thing about ALMA is that we actually just have a lot of what we call pads, the locations where the antennas can sit, and we can pick up the antennas with the transporter and move them from one pad to the other. And they sort of, on average, fall within these configurations, but basically we're not confined to exact antennas in exact positions. We can actually kind of grow and contract the array over a period of weeks and months. And so we follow this configuration schedule so that astronomers know more or less where the antennas will be in a given month, but it's basically always evolving. Just like one night or one day, move one antenna from one location to the next, and then another one from one to the next. So you're kind of playing this game of hopscotch and like rearranging the antennas all the time.
And how often is it not all 66 antennas together?
Actually, that's a really cool feature of ALMA. In fact, ALMA is basically 3 telescopes in one, because we can observe with different, we call them subarrays. So we have 66 antennas. As Faith already explained, we have some that are 12 meters in diameter, some that are 7 meters in diameter. And we can actually kind of pair or match up groups of antennas. So most of the 12-meter antennas can reach sort of the biggest, most distant pads basically, and form the biggest telescope. But some of those 12-meter antennas are actually confined to the central region, and they can observe at the same time that the other 12-meter antennas are observing. They can actually observe, and they get a different, they detect a different scale of object, basically. It's sort of like if you were a sports or a wildlife photographer, and you could use like the big zoom lens at the same time as like the normal lens, and you would see the same object, but sort of with different resolution. We can do that. And there's an intermediate array that is made up of the 7-meter antennas, and we can observe with that array at the same time as the other 2. So we can have 3 observations going at once, and basically it's sort of like observing the same or different objects with 3 different telescopes.
Right, that sounds very powerful. I can see why astronomers like ALMA.
And that's why we need that scheduling the scheduler algorithm as well, because you're kind of juggling a lot of balls at the same time to think, you know, how am I going to get all of these on target, all these different 3 arrays on target at the same time? Right. And that scheduler helps us figure it out.
Wow. Okay, I'm going to bring Loreto back in, and also Faith, who can help us identify some questions from the Q&A. But I just wanted to start by asking, like, both of you, what's sort of either the most exciting or wildest or most unexpected thing that kind of happened while you were an astronomer on duty?
Do you want to start? Go ahead, Adele.
I mean, I think that taking the picture of the black hole takes the cake. So Loreto is super lucky for having me here for that.
Yeah.
And I don't know if that's the coolest thing you've seen while you were at ALMA, but I'll let you go ahead if you're going to comment on that.
Yeah, no, I was going to say that being able to participate, you know, in this, okay, of course, the EHT and the black hole is the most, you know, famous, right, discovery that we've done, and famous because, you know, people that are not astronomers, right, also know about this. But there have been a lot more also, you know, very nice discoveries as well, you know, in other less with a lower profile, so projects with lower profile, but still really important for the community. And I guess that having the chance to be there, even if you don't, you don't know if they're going to be like a huge impact result or not, but you are contributing, right, to the community, to the science, by just taking, even if it doesn't matter that it's not my data, right, it's someone's data that it's very valuable. And so being able to participate in that way, I think it's great. But definitely the being there for the black hole image is like, oh, I was there, right? So that would be the coolest thing for me.
And I guess non-astronomical, the coolest thing that I see is wildlife. So on the drive up from the OSF to the AOS, it's like, I don't know, 30 kilometers, something like that. And it takes a little while, 30 minutes, 40 minutes. And there's one part where there's sometimes these vicuña, like sort of this version of a wild alpaca. And
I was going to ask, were those what was in the video?
Probably.
Sort of have them running.
Yeah, and then and there's this little kind of rabbit-like animal called a vizcacha, and they're very shy, and they blend in with the background. So, but if you pay attention, you'll find some, and the astronomers start to know, like, around that corner is a good chance you might see one. And one time I saw a condor that was just perched on a ledge, and like, I mean, it didn't even look real because it allowed us to get so close to it. I couldn't believe it. And it was huge. I mean, you know, condors are big, but when you see it close up and on the ground, you get that scale. And I mean, that was a remarkable sight. So you get to see some really amazing things in nature that you might not be exposed to otherwise when you go to observe.
Wow. Yeah, at the VLA, the birds are basically barn swallows, and they're like this big. Faith, do you want to ask one of the questions from the Q&A?
Sure. So this is kind of related to something Adele just answered, but what do all 60 antennas work simultaneously or alternate? Because you established that they work in different subarrays, but I think this person's also asking, like, if they're running at the same time or if they trade off or how that works. True.
So the antennas do operate in the subarray mode, so we can observe up to 3 projects at once. And the correlator, which is this computer that kind of combines all of the signal between all the antennas, is equipped to actually be taking data from those 3 subarrays at the same time. So you can be observing 3 different targets, different directions on the sky at the same time. And the correlator is gathering all that data in an organized way and able to make those observations concurrently.
Now we do have a campaign, as I mentioned before, we have campaigns of different types. We have a campaign for the VLBI, so very long baseline, so the EHT and the GMVA. We also have a campaign to observe the sun, all right? And when we observe the sun, I think, correct me if I'm wrong, we are using the largest amount of antennas at the same time for the same project. And I think that's really neat. So I think we can eventually, you know, combine them, but that's, you know, special cases. In general, the standard way that we observe is that we observe with the main array, so this one, and then the ACA and the total power, and so 3 different telescopes observing at the same time.
Yeah, definitely. ALMA took some, had some smart people designing it to make it this jack of all trades. It's sort of like a transformer. You can observe it. You can use, you know, all the antennas together. You can separate them and observe simultaneously. They're trying to be as, I guess, have as many features as possible using the same equipment.
Using the word transformer just now makes me imagine all of the antennas sort of like combining themselves into like a massive transformer antenna and then separating out all the time. I'll never not think of it that way now.
But you were going to say doing a dance, and they have some pretty cool videos of the antennas doing choreographed movements and then put some music to the background. It looks like the antennas are dancing together.
So that was a question from Antonio, and you actually also answered one from Paul about if you look at 3 different targets or a time, or like when you split it up into subarrays, or if all 3 are looking at the same target. I think also, in addition to looking at different targets, they can all be looking at the same target but in different frequencies too, right? That's another option for when you split it into subarrays. Okay, cool. And then another question we have is, have astronomers used ALMA plus other NRAO observatories at the same time to get more and better data? If so, what's an example of one of those projects? And that question's from Niels.
The first projects or type of project that come to mind is whenever they observe, for example, when they observe the gravitational waves, that they wanted to observe the same target, you know, with many, right? They observe it with many, many telescopes in many, many frequencies. And one of those, it was what we call also a DDT, right? And so a triggered project. So they trigger this. They say, hey, we need these observations. And so the observatory almost, you know, stops doing everything else and observes that because it's a priority. It's not, you know, literally like that, but, you know, we make it a priority and gets observed as soon as possible. I guess that maybe answer the question. Now with NRAO telescopes, I don't know if they've done simultaneous observations. So basically, you know, at the same time observing with NRAO and with ALMA. But definitely combined observations.
Yeah, I think they've definitely hooked the VLA and the VLBA together.
Oh yeah, absolutely.
I just don't know if they've ever done the VLBA and ALMA together, or
right, the simultaneous. Yeah. So yeah, and so that the people understand, you need simultaneous things, right? Because you need to observe what is happening. So these are events that vary with time where, you know, half hour, 10 minutes, 1 hour, right? Not all the things that change in like many, many years. And so that's why you need to observe them simultaneously, so that, you know, if you see something becoming bright in, you know, ultraviolet, you want to see if it's becoming bright also in the radio, right? And understand that tells you about the physics that it's happening in those events.
And I would think maybe that the VLA and ALMA, or the Northern Hemisphere ones and the Southern Hemisphere ones, can't always observe at the same time depending on where the source is, because they see different parts of the sky and just have a small overlap.
Exactly. And
so clearly the M87 is in that overlap.
Yeah.
Okay, and then here's one. How from an anonymous attendee, how does observing at different frequencies help? Higher the frequency, higher the loss in atmospheric interference and poor SNR. How is the issue handled? Of like, since I think ALMA goes up into the infrared a bit, so I think it's like, how does observing at the different frequencies help, and how is the issue handled that some of the frequencies have a harder time traveling through our atmosphere?
I guess that relates to how we schedule the projects that we want to observe. It's true that the higher frequencies on ALMA are the more challenging to observe, because you need the atmosphere to be extremely dry. Like, think about the driest days you can imagine. I mean, that you've experienced wherever you live, when your hands are getting very dry and you just know there's just not a lot of moisture in the air. That's what we need at the ALMA site in order to observe the higher frequency projects. So that depends on weather throughout the year. And basically, when we see that it's going to be a very dry night, then we prioritize the projects that are higher frequency. And when we see that it's going to be a kind of average day or night, then we can observe any of the projects available. And the reason why it's important to observe an object at different frequencies, it kind of relates to what to the picture we looked at of ARP 220 with Loreto. Actually, at different frequencies, you see different features in the object itself. That's related to the temperature of that area of the object. And so you noticed that in the ALMA image, you saw something totally different than you saw with the Hubble image. And even with different ALMA observations, you can see different types of shapes and different phenomena happening. So that's because the temperatures are kind of varying throughout different objects in the sky, and you can detect that with different frequencies. It's sort of like tuning the radio in your car. You actually can catch on to different stations just by changing the frequency that your radio is tuned to. So we're tuning our radio to see different frequencies of light, and we can then see different areas of the regions that we're trying to study.
So one thing that I wanted to add is that it's key what you said, Adele, about knowing how humid the atmosphere is going to be, is that we actually monitor, right, how much water vapor we have. And that tells us how ideal, it's the observations at that moment to observe at those high frequencies that are harder, that, the atmosphere is more opaque to the radio emission. At the very high end towards the infrared, it's more opaque. And so you need really, really stable and dry conditions at those moments. And we have the instruments to measure, right, how much of water vapor we have in the atmosphere. Of course, this is not exact. It's like, okay, we know more or less, and then we say, okay, it's a good night to observe these very high frequency. And we don't have too many of those at the very high end. And so we prioritize them whenever we have them.
Okay, I'm going to ask one more question because we're running out of time. But I mean, I could stand here and ask you guys cool stuff all afternoon. But this is a good question because I'm curious. At the VLA, we have fiber optics running from each antenna to the control building and right into the correlator. And if the control room for ALMA is at a completely different elevation than the antennas, how is the data transmitted from the antennas to the correlator? Is the correlator also at the 9,000 feet location? Well,
this is engineering feat, I would say, but we just have a lot of fiber optic cables, and they had to be designed and installed and buried in very careful ways. So the antennas are connected to the correlator. That correlator is one of the highest elevation supercomputers in the world. And so a lot of the computing is done there, but you still need to get the data in the hands of the people that need it. So you then pass the data down fiber optic cable down to the 10,000 foot site, the OSF, from the AOS to the OSF, we're talking 30, 40 kilometers or something of fiber optic cable. And then it still has to get to Santiago, and then it has to get around the world. So we're parts of these educational networks, these kind of internet networks that connect educational facilities around the world. And we hop on their path from the north of Chile down to Santiago, take a trip around Santiago to get to some sort of hubs of network connection. And then from there, the data travel to Japan, to Charlottesville, and to Europe. And the cool thing is that we then, because the data have taken this long circuitous path, we have 4 copies of the data in the world. So if there's ever a hiccup on one of them, we can kind of take the long way around and get the data still to the astronomers that need it. That's amazing. I never would have guessed that it was still. I wouldn't have either. There's a really amazing network of all of this data flying around the world, not just for astronomy, but other purposes as well. Well, thank you so much, Loreto and Adele, for your time on a Saturday. It's much appreciated.
I'm going to hand it back to Faith to wrap up. And yeah, we can't thank you enough. I think everyone really enjoyed hearing from you.
This was fun. Thanks.
Thank you so much for the invitation.
Yes, thank you. And now, for those of you who want to find out more about ALMA, NRAO does have some website features. So on our, if you go to our website and you go to this Explore page in the upper right-hand corner here, one of the options that you can click on is this ALMA Explorer. And that has a lot of short videos that you can watch that show you about the area surrounding ALMA and about the operations site and the telescope site. A lot of them can get more technical and are more behind the scenes than we're able to do in just a 1-hour tour. So if you have more technical questions or want to get more of a behind the scenes look, this is a good place to go. And thanks so much, Montana, for posting that in the chat. And then a few other things that you can find here. Right now, ALMA is not currently up and running and observing, and so this isn't up to date. But when ALMA is fully observing, there is a mission control that you can go to. It actually is a mission control for both ALMA and our telescope here in New Mexico, the Very Large Array. And the mission control shows you what both of these telescopes are currently looking at and what both of their previous 2 observations were looking at. So once things get back up and fully running again, then this is kind of a live look at what ALMA is doing. And this same page also has a list of different press releases, news about discoveries that ALMA has made and that the VLA has made. And the ALMA site has a webcam, it's 360-degree view, and it's interactive, so you can move the webcam, turn it around as much as you'd like. This is just a screenshot from it. And again, right now that may not currently be live, but when everything is fully up and running, then it updates every few seconds and it gives you a live view of what the antennas at ALMA are doing. And then lastly, I know visiting the ALMA site, since it's down in Chile, is not possible for everyone who would be present at our tour today. But if you do, if you are in Chile or near Chile, or you get the chance to travel there sometime, normally when during not pandemic times, when everything is fully operational, ALMA does have guided tours for the public at the OSF site here, where the visitor center is. They take you inside the building, they show you a visitor antenna like this, and they have these tours in both Spanish and English. So if you ever get the chance to visit ALMA, you can take a guided tour there. And so thank you everyone so much for coming today. And so we're doing themed tours every month. So this month our theme was ALMA. And next month, then we're going to do a tour on the 28th of February. And again, that'll be at 1 p.m. Mountain Time. And this time it's going to focus on the Very Long Baseline Array, or VLBA, which was mentioned a little bit during our tour today. And we do have, if you'll stick around to complete a short survey, we do have a survey that would be helpful for anyone who is willing to complete that. And yeah, thank you everyone for coming. I hope you enjoyed today's tour.
Thank you, everyone. We hope to see you next month.